we are going to finish up section 2.4 today. I know it's been a marathon because this section has a lot in it, but we're going to kind of wrap it up and be able to kind of summarize and use this all going forward. So the third part of what this section is something called your antiderivative, which is just the reverse of a derivative, the opposite of a derivative. So basically going backwards in our derivative continuum, and we'll kind of look at that as we go here. So the first thing that we do need is kind of what's the rule or notation for this. So if we're given a function f, the function, and we are going to use a capital F, is called the antiderivative of that little f. So what that means is if I have a capital F and I take a derivative, I would go back to the little one. So to kind of draw this out, if I'm at f, so if I take a derivative, I would get f prime. So if we're going this way, we're taking a derivative. If I take what's called an antiderivative, and I'm at f, I would go back to capital F. Now we're not going to go past capital F. We can go, past this way to the second, the third, and the fourth derivative, but there's no notation prior to capital F, and we'll talk about what we can do if I want to take multiple antiderivatives. What would I do and how would that look? But we'll do that in a little bit. So let's start with something. Let's say we had f was this x squared, and I want to figure out what that antiderivative is. So just kind of thinking, we know our power rule. So I know that, if this is squared, the thing that I took a derivative to get this with had to be cubed. What's different is the idea of the constant. Because if I had x cubed, we'll say that was capital F, that means little f would be 3x squared. But notice I don't have the 3 here, which means that for capital F, we're going to have, it's not just power up and put the number out front like the power rule was. I am going to go up a power, but then I don't want that power there. So I'm actually going to go up a power and what's called over a power, or like a 1/3 is right there, because that's what would knock out that 3 to leave me x squared. The other really, really important thing with your antiderivative is you may have had a constant, because when you take a derivative of a constant, like let's say there's a 7 there, it would have gone to 0, which then there's nothing here to show that. And so what we always have whenever you take an antiderivative is you have a plus c at the end of it. Okay, now I'm going to highlight this, so we're going to do this. And let's take some smiley faces and definitely stars. You cannot forget plus c. Actually, in class, we will designate somebody to be, like, you're in charge of reminding people about plus c before you take a quiz, before you take your AP test. You're going to stand up at that AP test and say, hey, don't forget plus c. Because every time you take an antiderivative, you have to put plus c at the end, because when you take, again, so let's say this is capital F. When I take the derivative to get little f, this goes power out, power down, and then that would have gone to 0. And so there's that x squared plus that we started with before I put stars all over it. And so that is super important. Like, write yourself a giant note on the top of your paper. Whatever you got to do, you got to remember plus c. And we will do it a lot today. Okay, so kind of to generalize that rule that we had. So let's say our function is x to the k power. That means our capital F is x to the k plus 1. And then we're going to divide by that k plus 1 to undo the power out part of the derivative. And then we cannot forget our plus c. Another way to write this, and some people, you can have your preference. We're okay with either one. You can put it as a fraction up front with 1 over that. I generally use this because I can use the phrase up the power, over the power, and then obviously plus c. But so you up the power and then you over the power, or divide by that power. All right, let's run through some examples and then we'll try using this. So I have 5th power, so I start with notation wise. If I'm at f, my antiderivative is capital F. So I would, the 3's there, I would power up to 6, I would over 6. The 7x, I would power up to 5, I would over 5. I would power up to 3. Now I would over 3, but there was already a 3 there, so you're going to end up with a 9 there. Now 11, you really have x to the 0, so when you up the power, you power it up to 1, and then I'll write it, you over 1, and then I will not forget my plus c on here. Okay, now there is some simplifying we can do, so this is just a half, x to the 6, this is 7/5, x to the 5th, this would be 1/9 x cubed, this is just 11x, and then plus c, because there could have been a constant that zeroed out. So that would be your antiderivative. All right, let's try two that have some kind of weirdness to them. So we're going antiderivative. Now -2, when I power up, I would power up to -2 power, and then I would over -2. Okay, x go up to 5th over 5, and this was x to the 0, so I would power up to x plus c. All right, you do not have to simplify, that is fine. I know I kind of pulled some of my fractions out front. This is fine. I don't need you to simplify your negative power, just leave it. This process does work with fractions as well. So if I find big F here, now powering up would bring me to 5/2, and then I would over 5/2. Now notice I'm dividing by a fraction, so that I can also multiply by the reciprocal instead. So it'd be 2/5 x to the 5/2 plus c. So just be careful with some of those fractions and how they work. All right. There is one special antiderivative, and it is for 1 over x. The reason we have a special one is because when you have 1 over x, it's really x to the -1st. When you power up, you get x to the 0, and then you divide by 0. And that's a big no in all math classes. You can't divide by 0. So it's not to say that it doesn't have one, we just have to restrict what our values are. And in our case, we're going to have x greater than 0. And so your antiderivative then is natural log with that plus c as well. Now, as we continue on in chapter 2, we're going to get a lot of different rules like this. So if you have a section in your notebook, if you want to get a note card or something and start keeping track of all like our special cases, like you're going to learn the derivative of sine and e to the x and all these other functions. And so if you want a place to start kind of tracking these, this would be the time to start that location. So that when you're doing your homework, you got them all in one spot. So again, this is saying that if your original is 1 over x, your antiderivative is the natural log of x plus c, and then it's only working for greater than 0. All right, so some reminders then. This is like that T-chart idea. And then these are kind of the columns. I made it 3 columns versus having to shift. And so this works, if it's F, F prime, F double prime, this can be F, this can be capital F, this can be F prime, and so forth on there, except for there's nothing after big F back with an antiderivative. But all of these T-chart processes still work. If you have, position, velocity, acceleration, if you have an inflection point on big F, that's a 0, or a max or a min on little f, that's a 0 with a sign change on f prime. So this is already kind of on that T-chart that you have, just it can work with f now, capital F. Okay, so here's this continuum that, it goes big F now, little f, f prime, f double prime, etc. Reminders, you still have this notation. So if I were to write this, this is your third derivative. Maybe I'll put an F here so it matches the other ones. And now a derivative is going to take you forward. Your antiderivative rule is going to take you backwards. So that's going to be our pattern here. All right, so let's use this now. So I want to construct a polynomial with exactly 2 stationary points at 1 and -1. So my original is going to have I want stationary points on here. Okay, and then those are the x values that I want them at, so plus or minus 1. Now I can't make a function just off of that, just having it be a stationary point, because remember a stationary point is where your derivative equals 0. And so if I have a stationary point, my derivative needs to be equal to 0 at those two locations. So I'm actually going to start with my derivative building. So I'm going to start with, let's call it f prime. And so I would have, since I want those to be zeros, I'll have x minus 1 and x plus 1. Okay. Now I want to get back to my original. So this is my derivative. I want back to the original. Now I can't do a power rule or the antiderivative version of the power rule because I have multiplication. So the first thing I need to do is just distribute. So x squared or FOIL minus 1. Notice I wrote f prime again because I've not taken a derivative, I've not taken an antiderivative, I've just simplified an equation. But now I want to go back and I want to figure out what was my original. So instead of writing f prime, I'm going to write f, and I'm going to use my up the power over the power. So up the power over the power, up the power to 1 over the power to 1, and then I don't forget my plus c. Okay, so this thing would then be, I'm going to write it as x 1/3 x cubed minus x plus c. So this is what we are going to call a general, there we go, solution because of the plus c. So c can be anything, so you're just giving a general solution for what it might be. Sometimes on your homework it asks for an example, so give me one example that has this. If they ask for that, you get to make up your own, oops, that's a 3. Whatever value for c you want. I was number 3 in college, so I'll say plus 3, or 17, or negative 1,000. You can pick. But you just pick a c. If it wants 2 examples, pick another different c. Whatever you want to be there. So this is your general solution because of the plus c. Specific or examples of solutions, you pick a c value, and then you're good to go. So just to kind of review here, because we're going to do this again with a different example, but it's going to give you some type of t-chart, and what's going to happen is you're going to create one of the derivatives and then have to take antiderivatives to get back to that original function that would have had this property. So let's do one more. Find the equations for some cubic curves with points of inflection at 0. Okay, so I got points of inflection. So I'm going to think my t-chart here. So I got f, constant inflection point. That means f prime is a min max. Now I can't make an equation with a min and max, so I'm actually going to go to my second derivative, and I want that to be 0 and have a sign change, and I want that to occur at x equals 0. So my second derivative needs to be something that when I plug 0 in, I get 0 out. So I'm just going to make up 6x, 3x. Well, you can just use x. You just basically need something with only x. So when I plug 0 in, I get 0 out. Okay, and I also need a sign change. Well, I know this is a line with a slope of 6, and I'm going through 0. So I know I'm going like this, so I definitely have that sign change that's needed. Now, I want the original, so I got to go backwards or take an antiderivative. So I'm going to up the power to squared. I'm going to over the power, which would be 6 over 2, so 3. And then I would get a plus c. Okay. Now, f prime is still not my original, so I need to go back to f. So I'm going to up the power over the power. So I would have 3x cubed over 3. Now, notice I have a c, which is a constant. When I up the power, it would go to x, because the constant goes up to linear. Now, I still need another plus c. Now, looking at this, it looks like the c's have to be the same. They don't have to be the same thing. So I can make one c1, and maybe this one c2, or usually you put subscripts or put just a 1 on one of them. But you put some subscripts to show that they can be different values. So really you have this, so this would be x cubed plus cx, we'll do plus c1 because that 2 looks good. We'll use that. So again, here's my general. Maybe it wants 2 examples or 2, then let's say x cubed plus 4x minus 187. There's one, and another one, x cubed minus 8x plus 10. See? So this would be 2 examples. This is your general solution. All right, that's it for the end of 2.4 here. Your assignment is listed on Canvas there, so go ahead and start that. I believe I named it as page 121. You might have some problems on page 120, but I wanted them to have different page numbers so that it wasn't confusing when you went to submit. So some of the problems might be on the page before, but it's just easier to kind of list them as separate things. Okay? All right, good luck. We'll see most of you tomorrow, Maroon Gold, and distance learners, let us know if you have questions.